Namaste and welcome to this lecture on mathematical foundations for machine learning. In the last class we looked at the idea of covariance, and we were basically looking at the joint moments of say two random variables in this case, and we are saying okay, we want to look at the ijth moment of a pair of random variables, and we also looked at sum of sum of expected values of sum of random variables and expected value of product of random variables and so on. And when we did the expected value of product of random variables, we said that look, E of x y is equal to E of x into E of y, and E of x y is called the 1/1th moment of the pair of random variables x y, and we gave it a name. We called it as correlation, and we said that if the correlation is 0, if E of x y is 0, then we said that the random variables are orthogonal to each other. And then we also looked at sum of random variables. That means if we have z to be a random variable which is sum of two random variables x and y, and we said that the variance of z, which is given by variance of x plus y, we figured out that there is a new term that comes into picture. I mean it is easy to see E of x squared minus E of x the whole square to be the variance of x, and then E of y squared minus E of y the whole square to be the variance of y. But then we also get a cross term in the sense which involves x y, which is 2 times E of x y minus 2 times E of x into E of y, and that is exactly what we termed as the covariance of x y. So we said that covariance of x y is nothing but expected value of x y minus expected value of x into expected value of y. And we said okay, there are other this one moments and all, and we said that covariance, if the covariance value is 0, we say that x and y are uncorrelated. And we also said that if x and y are independent random variables, then they will be necessarily uncorrelated. However, the converse was not true. We said that uncorrelated random variable does not or need not imply independence, and we just took a very interesting example. And we also looked at the Pythagoras theorem in a statistical version, where we said that if x and y are independent variables and independent random variables and z is equal to x plus y, then the variance of z is equal to variance of x plus variance of y. So we said that sigma z square is equal to sigma x squared plus sigma y squared, which is basically the Pythagoras theorem that we normally see in geometry and stuff. And we also said that look, independence implies 0 covariance, however 0 covariance does not imply independence. And we took a nice example. We said that in the xy plane we have 4 points which were marked like this: minus 1 0 0 1 1 0 and 0 minus 1, with all with equal probability. And we figured out that the covariance is 0 in this case. Expected value of x is 0, expected value of y is 0, covariance is 0, and we asked this question. Now the covariance is 0, does it actually mean that the random variables are independent? Our idea of independence comes from the idea of independence of event, where we say that if the events are independent, that means occurrence of one is going to give no update about the occurrence of the other. Now that same idea we will bring it here. Knowing the value of y, can we figure out the value of x? And in this particular example that we took, we said that the moment you tell me x is equal to minus 1 or plus 1, I know the value of y is equal to 0, and the moment you tell me the value of y is equal to plus or minus 1, I know that x is equal to 0. Therefore I get complete information about the random variable x, and therefore what we said is look, the two random variables x and y are not independent. That means uncorrelated random variables need not be independent, and that is where we emphasized that uncorrelated random variables need not be independent. But we also looked at one more interesting and important idea here, where we said we just took a deep look into the idea of covariance. When we looked at covariance suffers from a problem, and the problem is it is dependent on the units of measurement. We took this example where you measure the height and weight of people, a set of people, you say that the height is measured in centimeters and weight is measured in kilograms, and the covariance of x y, which is basically the product of E of x into E of y that you see here, basically tells that the unit of measurement for covariance is kg centimeters. We also had a problem here that if you are going to change the units of measurement to, let us say, pounds and inches, things are going to be a bit different, in the sense you might end up getting a different covariance number. So what we say is, like, in one place the covariance is like this, in the other place for the same set of quantities that you are measuring, the covariance is something else, which seems to be a bit hard to digest, because it is the same quantity after all that we measure. Therefore what we said is the problem comes here because it depends on the units of measurement. So what we said is, get rid of this unit of measurement, make it a dimensionless quantity. And so what we did, we basically got the standardized moment, the standardized moment that we had, which is basically x minus Ex by sigma x into y minus Ey divided by sigma y. That means x minus Ex by standard deviation x, y minus Ey minus standard deviation y by standard deviation y. The expected value of this product, we found that it just becomes a number without any dimension, and we call this expected value of x minus Ex by sigma x into y minus Ey by sigma y to be the correlation coefficient, and we finally we got the expression also for this, which we said the correlation coefficient sigma rho xy is equal to covariance of xy divided by standard deviation x, standard deviation y. Now what we are going to do is, we are going to make I mean, we are just going to observe this a bit detail and then try to understand what does it actually mean, and then what we will do is, we will go ahead with some interesting ideas related to this covariance and correlation and stuff. I will just give you a small introduction to the idea of covariance matrix, which anyway we will be seeing in the next week's module. Okay. So where do we go from here? Recall that rho x comma y is nothing but covariance of x comma y divided by standard deviation x, standard deviation y. And how did we get to this? We said that this is nothing but expected value of x minus expected value of x by sigma x into y minus expected value of y divided by sigma y. This is what we had. So let's ask a few questions here. What is that? If you look at x minus Ex and divided by sigma x and y minus Ey divided by sigma y, one thing that we see here is basically that you are dividing this x minus Ex by the standard deviation. That means you are basically normalizing it. It is basically saying that I have a vector and I want to get a unit vector in that direction. So what I would do is, I would basically divide that vector by the length of the vector to get a unit vector in that direction. So essentially what we do is, we end up getting in this case x minus Ex by sigma x would basically have variance is equal to 1. This is what you will see in statistics as the standard normal variable, the standard normal distribution, where the standard deviation, the variance is going to be 1. So that is basically by the z score that typically people do is basically x minus mu x divided by sigma, and z has unit variance and 0 mean. So this is what we are looking at. So something similar to that is what we do here. So if you look at this, we have expected value of this x minus Ex by sigma x into y minus Ey divided by sigma y. Now my question is, what are the values that rho xy can take? So what is the range of values that rho xy can take? right. This is one question that we need to answer. So, what is the set of values, because when you say x is going to have its own variance and standard deviation and stuff, when you say y it is going to have its own standard deviation and variance. Therefore, but what we do is we are just looking for this covariance divided by standard deviation x and standard deviation y. We want to look at what is the value of rho x y. So, rho x y basically I will just tell you like the value that it takes. You can do a small calculation out here and then figure out that it is a value bit in this range. Okay. So, what we are going to say is we are going to say that rho x y is always a value which is between -1 and +1, right, or essentially we can even put this, we can say that in magnitude rho x y is always less than or equal to 1, right. You can use Cauchy-Schwarz inequality. Remember we did this in our vector space, and then you could use Cauchy-Schwarz inequality here and get the value of rho x y to be a value between -1 and +1. Now what we do is we just try to see a similarity between rho x y and something else that we have seen in vector, I mean our vector spaces, vector algebra and stuff. Recall that if so u and v are two vectors then the angle making an angle theta with the angle theta between them and let theta be the angle between them. Then we say this cos theta is equal to u dot b divided by magnitude u magnitude b. This is what it is, and we already know that the cos theta is going to be a value between -1 and +1. And if you look at the expression that we have had for the correlation coefficient, that also looks something similar to this, covariance of x y divided by sigma x sigma y less than or equal to +1. Now you can actually see a striking similarity between these two, and people typically use all this cosine similarity and stuff, which is basically dot product of the vectors divided by the magnitude of the two vectors. So you see that there is actually a close similarity, or there is a similarity between these two ideas, right. Now one more thing that we want to do look at here is basically say that look, what is the value, suppose if I have we have already said that rho x comma y is a value between -1 and +1, right. We have said that this is going to be a value between rho x y -1 and +1. Now what happens, what do we infer when rho x y is equal to -1? What do we infer when rho x y is equal to 0, and what do we infer about x comma y when rho x y is equal to +1? There are these are three cases that arise. One is, I mean we basically look at the extreme values which are -1 and +1, and then the middle value which is basically 0. So what does it mean to say the correlation coefficient is -1, and what does it mean to say the correlation coefficient is +1, and what does it mean to say that the correlation coefficient is 0, right. So let us look at what happens here. You remember in the last class we said that the correlation coefficient is going to measure linear relationship between the two random variables x and y, and we said that if the correlation is 0, we say that look we say that it is I mean they are uncorrelated. The uncorrelated in this case mean that look they are not, I mean you do not find a linear relationship between them. it could have any other nonlinear relation, but just that it cannot have a linear relation, right. Or I mean if you know that x and y are independent, then the correlation coefficient is going to be 0, right. So, we say that when rho x y is equal to -1, we are going to say this implies x and y are negatively correlated. Now, what do we mean by saying negatively correlated? That if x increases, y would decrease, and if y increases, x would decrease. This is the relationship. So, we are going to say that x increases implies y decreases. So, the relation is basically this. I would not say okay, x increases, y decreases, y increases, x decreases. A best example, you can ask students, they will find this interesting example. What is that? Every student is almost fond of bunking classes. For them, the attendance percentage is something which is very important, right. So, if you bunk more classes, your attendance percentage comes down. If you bunk less classes, your attendance percentage goes up. So, you can take attendance percentage to be a random variable and the number of classes that you bunk to be another random variable. So, you say that if the number of classes that you bunk increases, the attendance percentage decreases. If the number of classes that you bunk is less, the attendance percentage increases. So, that is basically a negative correlated negative correlation between the random variables x and y. Now, what about rho x y is equal to +1? In this case, we are going to say x and y are positively correlated. That means if x increases, y also increases. If x decreases, y also decreases. Now, an example for this, you look at the number of classes that you attend and the number of and the attendance percentage. If you attend more number of classes, your attendance percentage is going to be more. If you attend less number of classes, the attendance percentage is going to be less, right. In the first case, we said if you bunk more number, that means if you do not attend, the number of classes that you do not attend and the attendance percentage basically are negatively correlated, and x and y, the number of classes you attend and the attendance percentage, these are positively correlated, strongly positively correlated and strongly negatively correlated. What about this guy when rho x y is equal to 0? This is a very tricky guy. We saw that in the previous example that rho x y was 0, the covariance was 0. So, if you look at rho x y, it is covariance of x y divided by standard deviation x, standard deviation y. So, the covariance of x y is 0. Now, what does that mean? They are uncorrelated. You can also say that the relation is basically nonlinear, which rho x y is not able to capture. So, this when rho x y is 0, we say that x and y are uncorrelated. Is that clear? So, this makes it very interesting. So, if rho x y is not equal to 0, then you say that x and y are correlated. If rho x y is 0, then you call them uncorrelated, and we know that independent random variables are uncorrelated. Let us rewrite here. Okay, if I write this, then people may actually look at the converse also, but then I will write the other part of the statement also. So, independent RVs or random variables are uncorrelated. Uncorrelated random variables need not be independent. Need not be independent. So, now we come to a question, why do we always say that independent random variables are always uncorrelated and uncorrelated random variables need not be independent? Does that mean that we have certain random variables which become when they are uncorrelated they are also independent? So, that is the question that we want to ask. So, what are we going to ask? We are going to say, are there do there exist pairs of random variables, or does there exist a pair of random variable? Let us look at this. Does there exist pair of random variables, let us say x and y, such that if they are uncorrelated, they are necessarily independent. Remember, independence implies uncorrelated, uncorrelated need not imply independent. Now, the question that we ask is, since we have used this particular phrase in our thing, need not be independent, we ask this question. So, does there exist a pair of random variables such that if they are uncorrelated they are necessarily independent, and that is the question that we are going to answer now. For that, I am going to write a very a huge page long mathematical expression now, and from there we are going to figure out what happens. Okay. So, just do not get panic with the expression that I am going to write as far as this this particular question is concerned. I am going to write a mathematical expression, do not feel panicked or anything, it is pretty simple, and what we are going to do is we are going to look at jointly Gaussian distributed random variables, jointly Gaussian distributed random variables. Now, what do we mean by saying jointly Gaussian distributed random variables? That means the joint PDF is going to be a Gaussian. So, this implies the joint PDF, the joint probability density function is Gaussian. So, what are we going to do? We are going to look at this recall. If x is a Gaussian distributed random variable, with mean mu and variance sigma square, then the probability density function f x of x was given to be 1 by sigma root 2 pi e power minus of x minus mu the whole square divided by 2 sigma square minus infinity less than x less than infinity. In this range, this is what we have, right. In fact, okay. So, now what we will do is we look at jointly Gaussian distributed random variable. So, what is the joint PDF? Joint PDF of bivariate Gaussian, that means you have two variables which are Gaussian. So, this. So, what is it going to be? I am going to write this as f x comma y of x comma y is equal to 1 by 2 pi sigma x sigma y into square root of 1 minus rho square e to the power minus of 1 by 2 into 1 minus rho the whole square, the whole thing into x minus mu x divided by sigma x the whole square minus 2 times rho into x minus mu x by sigma x into y minus mu y by sigma y plus y minus mu y divided by sigma y the whole square. Okay. That is what is going to be my joint Gaussian PDF. It is a bit scary expression that you see here. You have too many things, I mean even to understand that x minus mu the whole square divided by 2 sigma square is going to be a bit difficult. Now what we do is we have written a page long formula here and we say that look, this is the joint PDF for the bivariate Gaussian, where let us write all those terms that are involved here. We need to know what these terms are. So where mu x and mu y are the mean of x and y respectively, sigma x and sigma y are standard deviations of expected x and y respectively, and rho is basically the correlation coefficient. Rho is basically the correlation coefficient. Now let us look at uncorrelated Gaussian. So uncorrelated Gaussian implies, okay, the uncorrelated x and y implies rho is equal to 0. So therefore what do I have? I have x comma y of x comma y is equal to 1 by 2 pi. In this expression if you substitute rho is equal to 0, this term gets knocked off, this term gets knocked off, this entire term gets knocked off, and what we have is only this. So let us do this. So what we have is basically the following: 1 by 2 pi sigma 1 sigma 2 e to the power of minus 1 by 2 into x minus mu x by sigma x the whole square plus y minus mu y by sigma y the whole square, right. This is what we have. Now what does this mean? I can write this as 1 by this 2 pi, I can write it as sigma 1 sigma 2. Okay, let me do it this way. Okay, I can rewrite this as sigma 1 into root 2 pi into sigma 2 into root 2 pi e to the minus half of x minus mu x by sigma x the whole square into e to the minus half of y minus mu y by sigma y the whole square. This is what we have. Now you can see very clearly that this is going to be, you can write this as 1 by sigma, okay, sigma x, I am sorry, this is sigma x, sigma x sigma y, sigma x sigma y. So I am going to write this sigma x square root of 2 pi e to the minus of x minus mu x the whole square divided by 2 sigma x square into 1 by sigma y root 2 pi e to the minus of y minus mu y the whole square divided by 2 sigma y square, 2 sigma y that is a standard deviation square. So let me put it this way, the variance basically. So what is this? this is nothing but my f(x) of x and this is nothing but my f(y) of y, the marginal density function. So, what do we see here? We see that this implies f(x(y) of x comma y is equal to f(x) of x into f(y) of y. That means the moment the Gaussian random variables are uncorrelated, the joint Gaussian distribution, the joint PDF becomes product of the marginal PDFs, and we know that if the joint PDF is equal to the product of marginals or the marginal PDF, then the random variables x and y are independent. Therefore, what we say is, we say that uncorrelated Gaussian random variables, uncorrelated Gaussian random variables are necessarily independent, right. We are going to say uncorrelated Gaussian random variables are necessarily independent. Throughout this the lectures on probability, we have actually seen statements like this. What was that? We started with saying impossible events have 0 probability, 0 probability events need not be impossible. Now we say that independent random variables are uncorrelated, uncorrelated random variables need not be independent. So you end up seeing statements like this. So you say that, okay, in the forward direction it works, the reverse direction that you go, you end up seeing that it is not true always, but it is true in certain cases, right. So this is very interesting about probability ideas as such. Okay. So we figured out that the answer to the question that we had asked, does there exist a pair of random variables such that if they are uncorrelated they are necessarily independent? The answer is of course yes, we just saw that. The answer is yes, and what does it mean? That yes, the answer is if you have a pair of uncorrelated Gaussian random variables, they are necessarily independent, right. So that is one important takeaway that we have here. Okay. What are the other things? So we have seen the, okay, let us see, first of all let us look at how does this jointly Gaussian distributed random variable look like, then we will be able to understand a few more things, right. We can talk about more correlation and stuff, and we will have one more property, important property that we just want to make comment on. So what we will do is we will say this, and then we will okay, we will do this Gaussian and then we will go to that statement, making that statement, then we will start with our idea of conditioning of random variables. So how does this PDF, so how does the PDF of jointly Gaussian distributed random variables look like? We know that in the single random variable case it is going to look like this, centered about the mean. So we are going to say that, okay, this is infinity, this is minus infinity, you say this is f(x) of x and this is mean. Now how does it look like in the joint cases? That means you have bivariate Gaussian, how does it look like? That is pretty interesting. If you have observed cowboy's hat, the way the cowboy's hat look like, that is exactly how this is going to, the joint Gaussian distribution also is going to look like. Now what do we mean by that? Recall that the joint Gaussian distribution or the f(x) y of x comma y is basically saying z is equal to f x comma y of x comma y. That means you are going to plot this as a 3D surface plot, right. Z, the function is plotted along the z direction and you have the variables x and y in the xy plane. Z, along the z direction you plot the function. So it is going to look more or less like a cowboy hat, is that clear. So it is going to look something like this. The other would go like this. So typically what you would see is you would see something like this. In 3D it could I mean we will see it in the visualization, this would actually look like something like this, right. So I have my x and y direction and then the z direction also. So this is how it is going to look like. And interestingly we will see these contours and other things. We will probably try to spend some time on Gaussian later when we do the covariance matrix, because we want to look at this jointly correlated Gaussian and we want to decorrelate them and then say that they become independent answers. So one more important point as far as correlation is concerned, we will just write this, a very important idea that we should have in mind: correlation between random variables does not imply a causal relationship between them. That means if you say that the examples that we took, say you bunk the number of classes, your attendance percentage goes down, in which case you see that there is a correlation between the number of classes you bunk and the attendance percentage that you have, and it is also a cause and effect relation kind of that you have. What is that? It says that if you bunk more number of classes, the effect will be your attendance percentage going down. So that is a causal relation that you have, but it need not necessarily be the case where when you find correlation there could actually be a causal relation. It need not, you need not have. So you cannot interpret that when there is a correlation there is actually a causal relationship or causation. So correlation does not imply causation. Let us write that: correlation does not mean causation. Okay. This is very important. I mean, you can see, you can plot some two different variables and see that there is going to be a proper relation between these two, and then immediately we will be tempted to say that, look, oh, this keeps increasing therefore that also increases. It does not make sense that way. Is that clear? Correlation does not mean causation. Yeah, okay. So we have done all these things. Where are we going from here? That is a very important question. We looked at the joint behavior of random variables. We said that the joint behavior is captured by the joint probability mass function, the joint probability density function, joint CDF, joint moments, and so on and so forth. And we also studied the relationship between the random variables, saying that you have this correlation coefficient which looks at the linear relationship between the two random variables, and we say that if the correlation is 0, they are correlation coefficient is 0, the covariance is 0, then we said that the random variables are uncorrelated. And if the correlation is 0, that is expected value of x y is equal to 0, then you said that the random variables are basically orthogonal. So we have studied the joint behavior, we have studied the joint moments, we have done everything. We just need to do one more stuff. What is that? Recall when we did the idea of events, we took P of A intersection B to be the probability of A and B occurring together, and that is precisely what we captured in terms of the joint PMF, joint PDF, etc. in case of random variables, right. When we said joint probability mass function, we said P of x is equal to x intersection y is equal to y, that means P of x equal to x and y is equal to y. That means we took this event A to be x equal to x and event B to be y equal to y. So we were able to relate our event idea of the joint probability mass function idea, we were able to look at it from the probability of two events happening together, that means P of A and B, that means P of A intersection B, the probability of the event A and B happening together, we were able to map it to the idea of random variables. And in the same direction or along the same lines, we were also looking at this. What was that? If A and B are independent, then the probability of them happening together, that means P of A intersection B is equal to P of A into P of B. This is what we saw when we looked at independence of events. If you look at independence of random variables, that is exactly what we have here also. That means your joint probability mass function must be equal to the probability, the product of the marginal probability mass functions at each and every point that x comma y that you have. And we also said that if it is in the case of continuous random variable, independence implies the joint probability density function is equal to the product of the marginal density functions. Well, fantastic, all these things we have understood. There is one thing that we have not done here. What is that? Conditional probability, which we studied in the case of events. We said that we want to look at probability of A given B, that means I want to know if I can update my knowledge about A upon knowing that the event B has occurred. So we said P of A given B, that is the conditional probability or the posterior probability of A given B to be equal to P of A intersection B divided by P of B. So we looked at conditioning of events, that means knowing that one event has occurred, I want to find out what is the update that I can get about the other event. In fact, we said that if they are independent, we said that you can't get any information at all, therefore P of A intersection B is equal to P of A into P of B, which we interpreted as the posterior probability of A given B to be equal to the prior probability of A. That means occurrence of event B has not given any new information for me to update about the event A. In case of random variables also, we have studied the joint probability mass function, joint probability density function and so on. Therefore, can I do or can I look at conditioning of random variables along the lines of conditioning of events? Is that a possibility? If that is the case, what notion of conditioning we have here? Is the conditioning of random variable over the other the same as what we studied in terms of, is similar to what we studied in terms of events, or is it the only thing that is going to exist? Like you take I know that this is the feature that I have, given that this particular the sample that I have taken has this feature, what is the probability that it also has the other feature, let us say x, which we typically do in your machine learning. So that is your conditioning of random variables. Now, so in case of conditioning, is it always conditioning of a random variable with respect to another one, or is there something else that exists? So what we will do is we will break now for the class, and in the next lecture we will spend time on conditioning of random variables. Namaste.